Our next speaker is Kaishap Chitta, who is a PhD student at the University of Tübingen in Germany in the Autonomous Vision Group under Professor Andreas Geiger. Kaishap's research revolves around data-driven solution for decision-making tasks, particularly focusing on self-driving vehicles. And his work explores how autonomous agents can employ attention-based deep neural nets for safe navigation. And Kaishap is also interested in constructing data-driven simulators for robust policy learning. Let's please welcome Kaishap. I can move this a little bit out of the way, and then you can have your mic. I'll tell you when 5 minutes are.
Okay. Oh, I have a technical issue. 1 second. Yeah, I think I may need to reboot. Maybe I can try like that. Okay. Yeah. So I have a weird setup here, but let's see how it goes. So yeah, I'm going to talk about end-to-end driving with attention. And I want to start with sort of like breaking news fresh from archive. It's from 2 weeks ago. A team of researchers from Baidu proposed autonomous driving system with an MLP, like a 2-layer MLP, which was trained on nuScenes, just taking in the last like few seconds of the ego history, this ego state thing as an input, and a high-level command, predicting a future trajectory for a certain time horizon. And like the really crazy thing is that this model is the state-of-the-art open loop planning model on nuScenes. So the 5 papers on the left are all published at CVPR, ECCV, ICCV over the last 2-3 years. And those all incorporate some end-to-end input. So they have either cameras or LiDARs as some input information. But this model at the bottom, which was from this work here, actually got a much lower displacement error and lower collision rates on nuScenes. And the method doesn't take any perceptual input, just has this ego states as its input. So what does this mean? So I think like this kind of emphasizes a point which is probably well known to a lot of people here, but it's that open loop evaluation is flawed for planning and for self-driving stacks when you look at the complete stack. So there's many reasons for this. The main one being that planning is multimodal. So if you have a data set where the white car is you, maybe you observed in the data set this red trajectory where you merge into the lane a bit later, but it turns out your planner predicts this white trajectory, which is perfectly reasonable, but very far away from the endpoint of this red recorded trajectory. And so what that means is if you measure the performance of your planning systems based on only the predictions of your model in states that were observed in your data set, your evaluation is going to be flawed and you will end up with weird results like what we saw on the previous slide. So this kind of motivates what we do. Our experimental setup for testing end-to-end driving systems, planning systems, is through closed loop evaluation. And specifically, like, we work with an open source simulator because it lets you benchmark and compare things across the community. This is called CARLA. And the task in CARLA is to kind of drive from a start point, which is this little green thing, over a long route, which may be like 2-3 kilometers long, where you intermittently get these checkpoints along the way for how to travel along this route. And these little exclamation marks are kind of manually designed dangerous scenarios that are mined and designed by the simulator team. It's not ideal, it doesn't capture all the dangerous situations you will see in this long tail that we've observed in the last few talks. But at least it gives a way to evaluate models for the actual driving performance and not a distance on an observed data set. So specifically, like how you evaluate in CARLA is that you run your trained driving system over a number of routes, that's the N here, and you multiply two things, the completion, which is how far you got to the end of the route. So getting to the end is a 100 score there, so it's a percentage. And there's a penalty for infractions. This is a multiplier that's applied every time you make an infraction like colliding, running a traffic light, and so on. Each time you make an infraction, your score gets multiplied by a number less than 1. So with that as the background, I want to talk about some of the ideas where we have worked on parts of end-to-end driving systems to improve their performance in this closed loop evaluation setup. I want to start with some work on sensor fusion. So there were some great talks on why it's good to have redundancy and have lots of sensors. So a very quick recap is that images and point clouds are complementary. Images have very dense inputs, and you include information there like traffic light states, which you need to drive, the semantic information basically. But they do not have a very large field of view, and 3D information is not super reliable in there. So that means if you want a pure image-based system, you're going to need a lot of cameras and a lot of compute to process all these cameras. And point clouds, they give you very high field of view 3D information, but again are not enough to solve the driving task by themselves because they're sparse. And in order to process these sort of complementary sensors, the most well-established way of fusing them is through geometric feature projections. I think BEV fusion, which was covered in one of the earlier talks, is a very popular way, or like any common feature space, and projecting these different sensors into a common feature space is a very popular way of fusing information from multiple sensors before processing it with the rest of your network. So I'm going to talk about a small disadvantage of geometry-based fusion. Consider this scenario. There's an intersection. You're about to enter the intersection, and you're seeing this camera image and this LiDAR sweep. So what happens is that if you do geometry-based fusion and you have a method that's like good at associating the camera and LiDAR, the features that you extract from these green traffic lights in the image, which is shown in this yellow box, are going to be mapped to the features that you extract from this blue area in the LiDAR. But what gets missed, and what another part of your network then needs to figure out, is that there are vehicles actually that you can see in the LiDAR here. These are the edges that you see in this red box. These vehicles are going to be affected by this traffic light and start moving into the intersection. And since the traffic light for the ego vehicle is also green, if you don't know about these vehicles moving, you're going to enter the intersection and be in a dangerous situation. So in these sorts of dangerous scenarios like unprotected turns, it would be useful if your feature fusion can do some kind of global reasoning as well, and not just do geometry-based mappings between your different sensors. So the first idea I'm going to quickly talk about is how you can use attention to do this feature fusion in a way that captures this global context. Yeah, so this method, it's an encoder for multimodal inputs, which we call TransFuser, which is a simple idea. You have CNNs for each modality that extract these features, but instead of doing a geometric mapping between them, you use transformers, like everybody's favorite building block these days. Transformers basically tokenize the feature maps at different resolutions in your CNN encoders and concatenate these into a sequence and residually sort of add back the global context encoded features before going to subsequent blocks in the architecture. So with this, we kind of built a end-to-end driving stack. So that was just the encoder, which is now compressed onto the left half of this figure. We train with multiple loss functions. We use perception labels for supervising the features of the image and LiDAR branches to contain like rich task relevant information, like how to predict the map, how to detect vehicles, or the depth in semantic segmentation in the case of image branch. But the main loss that sort of we focus on optimizing is through this decoder in the middle, where we're going to use a GRU to predict a set of waypoints, so future positions that were recorded in the data set, conditioned on a goal location that you want to reach in a short horizon. So this is trained end-to-end on a single data set with all the objectives, and then you can use a controller to steer throttle brake basically in your simulator for evaluation. So we set up this architecture and we started looking into it more deeply, and we found that there's actually a very interesting little detail. So I'm going to show some visualizations of the predictions you get from this model. You see the inputs, which are the image on the top and the LiDAR point cloud on the bottom. And I've also overlaid the ground truth map onto the LiDAR, so you can see where the road and lane markings are. The model's predictions are these blue points, the waypoints, and this red dot is the thing which I called the goal location, which was input to this model's decoder, which tells you how to drive. It's meant as an intention signal of whether you have to turn left, right, or go straight at an intersection, for example. So interestingly, we found that if you perturb these models, if you put them like far outside the center of the lane, maybe you face them on the sidewalk or in between the lanes, they always extrapolate their predictions straight towards this goal location input that was given to them. So specifically because we did testing in simulation, it's very easy to have like small localization errors, and these goal locations are very accurately in the middle of the lane. So it turns out that these sort of models just learn a shortcut that if the goal location is close enough, I should just drive straight into it. And this is the best way to stay within the road and get a good driving score. This is not just true of this TransFuser model I presented. We went over nearly all the state-of-the-art methods in CARLA. So on the left, there's a method called LAV, and the right, there's a method called TCP. And since all of them adopt the same sort of architecture where this goal location is kind of fed into the network really late in the architecture, and all the perception goes through these very big network encoders before being processed by the decoder. Even though they differ in terms of like how many waypoints they predict or some other details like what input modalities they have, all these methods are susceptible to kind of driving straight into the target location. And on the right, you can already see a problem that might happen because of this. If the target location is far enough away, like behind a turn in this case, the model's prediction is to kind of drive into the opposite lane because that is the path towards this target location. So we had a hypothesis that there is a problem with the encoder features which is causing the model to focus on this goal location unnecessarily for making its final prediction. So we made like a minor modification to how one specific aspect of the network architecture worked, replaced it with attention in order to preserve spatial information in the encoder features. I'll go over what that is and how it works quickly. So this is the same architecture as before. I've just flipped the image and BV branch so that's easier to visualize. What we did is we replaced this MLP that we had coming into the GRU decoder with a transformer decoder. So again, we see here the usefulness of these attention-based representations. What we do is essentially like instead of predicting waypoints from this pooled feature, so before you would have like this 8x8 feature grid coming from your network, do an average pooling, so you have a feature vector, and then feed this into your GRU decoder to predict waypoints. We used a transformer decoder where you learn a query that you have like one query corresponding to each waypoint you predict, and you use these queries as the initial features for your GRU instead of having a single feature coming from the encoder. So why was this idea even like in our head? Why do we think this makes sense? I'm showing here again a similar example for our TransFuser model where you have the image on the top, the goal location is behind a turn, and the model is predicting a set of waypoints that drive into the opposite lane and would crash. What this figure shows though is that instead of showing the actual map, I'm showing the prediction of the map that the encoder generates through this auxiliary head of BV segmentation here. You can see that the overall architecture has learned where the lane center is. The segmentation of the road seems correct. So the model knows that the lane it needs to follow is actually straight, but the waypoints still bias like the prediction towards this very sharp cut. And what that means is that the encoder features are powerful enough to include the information about the center of the lane, but the decoder is not able to access this, which is why it's relying on the shortcut of the target point. When you use this transformer decoder, you have the output then becoming what you see on the right, where you now see that the model is staying in the center of the lane. And this is mainly because the decoder can now learn to prioritize information from certain tokens in this bird's eye view feature map that basically preserves the spatial information in the feature and acts as a stronger correlation so that the network doesn't use the shortcut but uses the true causal reasoning for predicting the waypoints in the scene. We also, this is a minor point, but we found that another way to make these models robust to not cutting lanes and just directly following the target point is to use a lot of data augmentation. So this was an idea that was quite popular before the most recent set of CARLA papers, where if you have your simulator and you have the sample on the left where you're driving normally straight through the center of the lane, you can generate additional data by simply rendering images and LiDAR point clouds from slightly offset positions to with like shifts and rotations, and compensating the waypoints through a geometric transformation. So that was the two ideas that I just talked about. Now I'm going to show some results. So CARLA has this logistics benchmark, which is quite challenging. You have lots of weathers, long routes, and the metrics I talked about earlier. The completion is just how far you get to the end of the route, and the driving score is after multiplying these penalties for colliding and running traffic lights, for example. You see that the first idea I proposed of using global attention-based feature fusion over geometry was responsible for giving a huge boost in this driving score metric. So you don't actually drive to the destination much more, but you avoid many more collisions, and specifically because of these scenarios where you need to associate things between the image and the LiDAR, which are geometrically and in terms of modality very far away from each other. And the other change, which was adding the transformer decoder and the data augmentation, is responsible for another decent, like 45% improvement in this driving score to 71. The important thing is that this is actually a pretty big step forward in this field. Some of the most recent work, like over the last 3-4 conferences, have kind of saturated at a score of 60 on this benchmark. But like through just understanding the weakness of these like end-to-end models, these biases in them, we got a pretty big boost here to 71. All right, so I come to the summary now. So the main takeaway, if anything, that I would really hope everyone gets from this is that open loop evaluation is flawed. So until we have better simulators, I think working with the simulators we have is a good solution for end-to-end driving research and for research and planning. The attention-based sensor fusion idea is good at capturing global context, which can be useful for tasks like planning. And the attention-based feature pooling we introduced mitigates these shortcut learning mechanisms where you have very low dimensional inputs like this goal location contributing heavily to your model outputs. The code for all of this research is publicly available. You can find it at this link. We also are releasing a follow-up to this very shortly. I also want to quickly mention that end-to-end driving is a very rapidly growing field. So since 2016 or so, when it was kind of rediscovered in the deep learning age, there have been like over like 200 papers doing end-to-end learning, and one of the main things driving this is CARLA. We've had like very rapid progress on the CARLA benchmark over the last couple of years, and now there are new open source closed loop simulators like a second version of CARLA and something called nuPlan, which we also are really interested in, but unfortunately I couldn't talk about today in detail. 5 minutes. Yeah, I'm done. So I would say like this is like really exciting, and like given the other data-driven simulation approaches and improved simulation approaches we are seeing, I would really look forward to basically new solutions and new ideas over time. Yeah, so that is it. I wanted to thank all the team members who are on this project and everyone here for listening. Yeah, on the right you can access my website where we will be releasing like some new work in this area and also on the nuPlan benchmark that I very quickly mentioned. Yeah, so that's it from me, and yeah, thanks. Take any questions now.